Okay, so does that all look correct to everybody?
Yeah, now it looks good. Hopefully JP can make it.
Do you have the he3 use at hand, deck at hand if we need to take it today?
Yeah, there is still some final adjustment that should be maybe done today still, but I can probably have it if JP cannot make today.
So that's what we're moving to the end. It'll look the correct order now. That's today too. So the backup slides are my day 2 stuff. So okay, I'll get those in order this afternoon.
Yeah, I sent message to JP that he has been moved to the last speaker today, so if he can make it.
In.
Does that look correct to you all, or is that the slide?
That's the wrong one. Swap display.
Yeah, this is the Microsoft thing. Does that look correct? Perfect.
Aaron, I'm getting this meeting summary with AI companion is on. I've never seen that before. I'm going to stop the summary. I'm going to stop it. It looks like a feature of some sort.
I just saw that too. So
okay.
Yeah, I didn't turn anything on, or I don't believe I did.
All right. I'm going to stop it. All right, I think you can start anytime. We've got quite a contingent here.
Looks like there's quite a few on. So first of all, welcome everybody. Thank you for attending day one of the CSC Lumi Technical Showcase. Without too much further ado, just a few logistics things. The workshop event website is located here. That site includes the agenda, session abstract, and speaker bios. The presentation material will also be uploaded on the event website. And just a reminder that the working group website is also located here at the llnl.gov address. Also, non-speakers, please mute your microphones, turn off your webcams, and kind of limit the overall network bandwidth. Please use the Q&A or please use the chat box, not the Q&A button, and we'll moderate that. So, agenda for today, we have Lumi design and procurement, facility systems and operational data analytics, the Lumi use cases, current and future. And we may, very late in the day with some travel logistics, we have facility design and construction. We may switch that with heat reuse if JP is unable to make he's got a flight delay. So he will be joining as soon as he possibly can. So without further ado, jump into Lumi design and procurement.
All right, thank you. I'll share my screen. And can somebody confirm that you're seeing the slides?
It looks good.
All right, good morning, evening for us. I'm Pekka Manninen. I'm the Director of Science and Technology at CSC, and I've been in charge of the Lumi supercomputer from the day one. So today I'm gonna share you with some stories around from the journey. So with the title of system design, specification, and procurement, but I don't, well, probably it will be just like a random anecdotes, but let's see. So, but just to introduce what we are talking about today and tomorrow, Lumi supercomputer. So it's Europe's flagship supercomputer at the moment, and a part of a initiative called EuroHPC, which is the European Union initiative for building, basically to catch up US and Japan in terms of high performance computing. And the thing, it surfaced a bit over 5 years ago, with Lumi being part of the first generation of EuroHPC. And currently, the EuroHPC already has built 3 of these kind of like a top 10 systems.
1.0, and it did not play well with others, specifically.
Can everybody mute? Thank you. So there are currently 3 European or EU's systems in the top 10 of the 500. So one in Kajaani in Finland, one in Barcelona, Spain, and one in Bologna, Italy. And this is the story of the northernmost, that is Lumi. And Lumi has also a particular feature from the European perspective that is a joint effort of 10 countries. So that's a kind of like unheard of in Europe, that different countries would invest, or European HPC, that countries would invest in supercomputers outside their country borders. But Lumi is a kind of like a first of its kind, but by no means the last. And the idea is that there are these 10 countries, and nowadays also including the Netherlands. These countries, together with the European Union, are investing jointly to the system. So 50% of the money comes from the Union, 50% from these countries, and the shares of the resources goes accordingly for the countries. and they basically can share then further this allocate projects as they see fit. So how come the Commission decided to locate the system to well, not northern but mid part of Finland? Is that I think it's a site together with this collaboration where the key factors in this success. So as we are going to learn during this showcase event, Lumi is located in a former paper factory where the paper production has moved to Latin America a long time ago, but the site and its capabilities remain. So we took one of the empty paper machine halls and constructed this kind of like a building within a building, so data center inside this hall. And the kind of like figures for the site are very well self-explaining why it's a very good site of locating supercomputers. So the paper machines used to consume an immense amount of energy. So we have basically transformer capacity to the 200 megawatt range, and it's all we can operate it on a 100% hydroelectric energy, so carbon free fashion of the supercomputers. It's benefited by very reliable power grid, so no blackouts basically in the last 40 years, and the fact that the city's district heating plant is in the same site, so we can use all the excess heat for heating up the surrounding city, as I was going to explain later. But the story of Lumi so far. So, like I said, it's everything started to basically it's the project or the program is quite exactly 5 years old. But my timeline here starts from when the European Union decides to place one of the systems in Kajaani. This is in June 2019, and we started the system procurement in the late 2019, completing it in the summer of 2020. But then like going to elaborate it a bit more. It took all the way to October to have the contract in place. And if you remember, something happened in the early 2020, so the world went lockdown, and purchasing a system from kind of a remote video conferencing wasn't the sort of easiest task ever. But contract was in place. We got this facility ready in early 21, and were able to start the installations in June 21. And the first phase of the system was ready by the end of 21 and opened for customers, which is now the multi-core partition of the system. Was opened in the beginning of 22. Then other things in the world happened. So there was like a global shortage of microelectronics, and HPC installations took quite a bit of hit from this, and meaning that the second phase of the system was quite scarce in components. So all kind of like a small bits and pieces were missing from the plates, and we were able to deploy the second phase only during the summer of 22. And it hit the top 500 list for the first time in May 22, and reached its kind of a full capacity a bit over 1 year ago in November 22. And it's been in customer use for 1 year now. And with an addition that we then we kept on deploying different things to the system. So, for instance, the object storage system was opened last spring, and then we added a little bit more capacity to the both multi-core side and the GPU side in August and November this year. And now the system is finally its final configuration. So it hit the 380 petaflop value for the last top 500 list, and that it made it into the 5th spot. So this basically says it. So it's currently it's the this was the GPU partition big sustained performance, so HPL performance, and like I said, so it is made to the number 5 spot, and it's clearly the fastest in Europe. And also it's on the other lists, it holds the spots number 2 for the HPL AI list and the number 3 for the SPCG list. And what did we wanted to achieve with this system originally was to build a platform for convergence of traditional simulation science, HPC, AI that was in a very fast surge back in 2018, and then large-scale data analytics. But towards the technical goal and the vision, so some just thoughts from the what led us to this point is that I think we learned about this EuroHPC initiative in the fall of 2018. It landed on my desk that I need to lead it somewhere around that time frame. We realized that okay, Finland won't be able to invest the half of the needed budget, so we started calling our friends across Europe, and were able to build the consortium for deployment of the system. And so the first kind of like a design, or this technical design, needed to be in place for the when we were expressing to the European Commission that we would be willing to invest and host the system in Finland. And so basically the initial thoughts for how could the system look like, it already was presented 5 years ago now. It was a meeting in Helsinki in exactly 5 years ago. And there I used the slogan of Swiss Army knife, which basically means that you can like pull some kind of like a corkscrew or knife for pretty much everything that the science of this decade needs. And then the sustainability, so economical, so kind of a price performance, as well as like a ecological, so green way of thinking sustainability was, and the kind of a 10-country consortium collaboration were very integral parts of the narrative already from the beginning. But it turned out, or it was quite clear that the EuroHPC joint undertaking, or the European Commission that is, was very obsessed where do the lists, the systems that they are investing in, placed in the top 500 list, which basically made the system design on achieving very high HPL score. It was of course criticized, and we were thinking that okay, are we ready to do this? Are we ready to go for like a GPU only system, GPU heavy system? But then again, so I don't know if I would be able to go back in time and redesign. I don't know if it would be anything else. So the first idea of building this kind of a tier 0 GPU system, which is then complemented by still sizable but not like an extreme scale CPU partition, and where basically everything would be in a kind of integrated fashion. I don't think it would be any different. But the first kind of a boundary condition or driver for the system design was that we need to achieve very high SPL figure with the system, which of course drive the solution towards the GPU system. But anyway, we just wanted to achieve a system that has the Swiss Army knife thing, that you have different functionalities that we can then by combining this, we can support a very big mix of complex workflows that we thought would be relevant in few years, basically today. And we counted that we have the sites that were investing in the Lumi consortium. We counted that we have more than 20,000 users in our system. So we were expecting very large and varied in terms of the workloads, in terms of their skill set and so on, very varied user base. And then the next thing was that this basically the figure was what we presented part of the expression of interest. I drew it myself. It's not very pretty, but and I drew it with my some open office draw. So it's looks like that one. So later on, there have been graphical designers that made better pictures out of the concept. But this this picture went in to the expression of interest. And we were expecting on the kind of a back of an envelope that with our budget, we perhaps would be able to install a system that has it's very GPU heavy, so the accelerated partition would be over 2,700 nodes, and somewhere between around 1,200 dual socket nodes to complement it. And in fact, we didn't have very much room when the commission then started the procurement, because they were at the end of the day running the procurement, which may sound weird from the US perspective, where the Department of Energy is funding the systems and the sites are installing them. But here in the EU it works a bit differently. But so it was pretty much echoed to the first procurement documents, and we were of course fine with that one. And we were thinking that it would, in the expression of interest, we were listing a few use cases that we think that this system would be a very major asset. So they included AI accelerated data analysis, automotive industry, cancer research, climate modeling, computational fluid dynamics, life science, material science, and space weather. And when at the end of the day, we're not very far away from that, what actually is being done today with Lumi. So I know I'm a bit behind the schedule, but I think we will able to catch up. So the story went so that we eventually, when hosting agreements were in place and everything, we were able to start the three systems, in fact, the Spanish, Italian, and our system at the very same time as different lots to the same procurement. It started in November, and it started with a competitive dialogue fashion. So there were first round of requests to participate, where 4 vendors wanted to enroll the competition. We had the first round of negotiations and at first in a way submissions they need to do. We kept on giving feedback, enhancing our procurement documents during the spring, and of course, like you don't want to remember, but still remember that everybody were confined to their kitchen by their kitchen tables for many months at that point of time. And so suddenly we were able to do the negotiations just on an online fashion, and everything that was for instance, on this first phase, I needed to travel to Luxembourg to evaluate like a paper, like a submissions on a printed paper, because I don't know, the EU law didn't allow anything else, but suddenly after that there were no problem of having electronic submissions and reading them from home when there was a clear need for it. Then so 3 rounds of negotiations with the vendors, and final ITT was issued in May 2020, and only 2 vendors left the offer in June 2020, and then we got the evaluations ready was it at the end of June or beginning of July, but then something happened in the behind curtains in the European Commission, and it took forever for them to find the winners for these 3 lots. So one can only speculate what took so long from them. But we were just watching the paint to dry and crush to grow, and fine. But finally, we were able to sign the contract in October. And the procurement itself was done so that it was in base of technical value of 42% of the score coming from there. Cost performance analysis, which is basically benchmarks or application benchmarks, was 1/3 of it. Something called quality of services, and a little bit of a vague criteria called EU added value. So the Commission wanted to have this kind of political angle, so it wasn't only a technological driven purchase. And one thing that we did perhaps differently from our national procurements is that we had the supply chain evaluated as a part of the risk analysis and the quality of service score. So technical value basically was this kind of like a very long list of target requirements. They were had different weights, and the vendors were able to say it's 0, we won't go for it. It's 1 if they meet our requirement, or it was 2 if they go for an additional mile and put some so go for next level of something. And then when the points were counted, so it was we tried to keep it as kind of a numerical as possible, so there's no kind of a room for sort of questioning the outcome. And when the points were counted, the HPE Gray came out as a clear winner at the end of the day, so they got clearly more points. And this is the procured system, or the installed system. So there have been some delay penalties and things like this, but this is how the system looks today. So it consists of roughly 3,000 GPU nodes with the MI250. So it's the same node as in the Frontier supercomputer. So it has the 4 MIs and then the Trento CPU as a host. And then there's the 2,000 nodes of the Milan socket. So it's kind of an all AMD system. And then kind of a spicy. So we have a fairly large Kubernetes microservice platform, data analytics partition, and different kind of a service nodes. The storage is in 3 layers. So there's basically like a separate clusters for flash and a spinning disk. And so it's depending on the use case whether they benefit from the flash based storage or not. So they choose to use either of them. And then there's a data management service based on the Ceph technology. Also, it's been connected. It's not part of the deal, but we have also connected Lumi to quantum processors. And everything over here sits in a nicely in the slingshot interconnect. So it is basically one big slingshot for everything. And it has its pros and cons, but it's an at least we are closer to this kind of the original credo of this kind of convergence of different workflows, and or supports the convergence of different kind of like capabilities. But okay, so this kind of like a initiates us to the showcase. I think I can take a question or two, and then I hand over to Esa. So how would you characterize your job profile over time? Average nodes per job. Good question. I don't have a graphic from right away to give. But I would say that our average GPU node size is somewhere between 200 and 300 GPU nodes. So not, I think people have found this kind of sweet spot between the queuing time and the execution power. So we do have quite a bit of large scale jobs. sometimes we give the system for like a full system runs. So we do have applications that can scale over the whole GPU partition. And at the same time, there is this kind of high throughput workflows, and also cases where there's lots of small calculations being this kind of throughput fashion, but this kind of like a training a machine learning from the framework from in a kind of on the fly from this kind of high throughput cases. So there are this many kinds of like job sizes for anything from single core to 1000 GPU nodes would be but average somewhere like some hundreds of GPU nodes. Self-object storage attached to all nodes or a subset for AI. So it is visible to all nodes, and it's not. So we don't have the Deos layer ourselves. So the object storage is not with kind of like won't support very compute intensive cases. So we lack the kind of like the accelerated layer there in between, but it's more for like this kind of a dynamical data staging. So if there's a data set that you need to sync every day, or like there's this kind of like a evolving data set that you want to share outside the world, or like a import to for the compute all the time. So it's kind of it's open to the internet from basically both directions. So that's the use case for it. Track node utilization. We do system is pretty full at the moment. Why don't I just like a show it? If I go for I can even show it. So this would be, for instance, the last 30 days on the CPU side, GPU nodes. So some node unavailability, but now currently pretty much all the nodes are in use, in up and running and in use. So it's been pretty busy system from the start, and it's the same applies for the CPU side. So currently the queue situation is in control in a way that GPUs are utilized, but the queuing times are not excessive. Large, but on the CPU side, we kind of made some mistakes in the beginning, and there are too many projects on the system, so the queues are quite long at the moment. And it's been looking pretty much the same, so for quite some time. So we've been struggling with the node counts at times, but now we are finally to the where we are over the 95 or 97%, but it's been pretty much utilized all the time. Okay, should we move on to SI so that I will steal the whole evening?
Yeah, I think certainly if you have additional questions, there'll be more opportunity at the end. And yeah, let's move on to ESA. I'll share real quick. So yeah, we'll move the discussion on to facility systems and operational data analytics. And for that portion, we have Asa, who will walk us through that.
Okay, hello, good evening. I will share my screen. Just a second. So is it visible?
Yeah, it looks good.
Okay, so hello everyone. My name is Heiskanen. I'm working as the Lumi operations manager in the CSC IT Center for Science. and I'm going to tell you today about the facility system and operational data. So, as Pekka mentioned previously, the Lumi is installed on this old paper mill pit area where the paper production was announced to shut down in 2008. So it took a couple of years to transform this old paper mill area to in the current state where there is now a couple of data centers hosted and other businesses in place. So our national data centers moved into this area already in 2012. So those are located in this old paper warehouse. And the Lumi data center was installed in this old paper production building where one of the paper machines was hosted. So excess heat utilization was pretty clear solution and option when operating in this business park area, because we have this district heating power plant only a couple of 100 meters away from our data center. So excess heat utilization is pretty cost effective to do. This area has this national grid substation with over almost 1,000 megawatt installed capacity from the 60 different directions from national grid. And this is in the area we have already installed 230 megawatt of existing transformer capacity, which is already in place. So this is pretty solid in the network power distribution wise for this kind of HPC operations that Lumi is. And as Pekka mentioned earlier, that we have a lot of renewable energy. So there is a 3 hydropower plant in this river of Kajaani, and there is nowadays quite a much of wind power also implemented in the area. So a couple of details about the power distribution of this area. So the power distribution of this area is very reliable, and backup power generators are not required. In our case, we haven't implemented on national or on the Lumi data centers. So there is 6 different directions from the national grid that is can be fed to the area power. And in the area transformers, there is installed capacity at 230 megawatts currently, which is then fed the data center from 2 different sources. And only the critical components like cooling and storage and management systems are covered with the UPS. So HPC cabinets are running directly from the grid power. And this Kajaani-Kainuu area region is an energy surplus area where the power is produced from renewable sources like hydro and wind. So these are the availability numbers. So actual availability numbers from 92 to 2011. So this area main power distribution has 100% availability, and in the area it was still very, very reliable. So this is overview of the Lumi data center itself. So it has been done. We did a building inside the building. So this is the old paper machine building. So this is the latest paper machine that was installed into this building in 1984, and it was decommissioned in 2008. We have 5,800 square meters in the 3 floors, and our white space is about 800 square meters for the IT devices. Total power capacity is 15 megawatts at full build out. So data center itself is also 2 floors, so all the power connections and cooling pipes and network connections to the cabinets are coming beneath under the raised floor, which is 2.4 meter high, and all the electrical main equipment and all the cooling equipment is installed in the first floor. In this building, there is still over 14,000 square meters free space for the future expansions, so there could be fit a couple of more this size of data centers. Some numbers about this year, so these are from January to end of November. So our PUE average is 1.27, and we are able to operate down to the 1.05 PUE in the free cooling. But this PUE is increased because we are operating the heat pumps by ourselves. So energy reuse value average on this year has been 0.54, and energy reuse factor is 0.6. So every megawatt that we are spending energy, we are able to reuse it, 600 kilowatt of it. About the fire security of the data center, we have this data center protected with the Inergen gas extinguishing system, with Vesta, which is very early smoke detection appliance. And this whole building is also protected with the Vesta. Technical spaces in the first floor is protected with the sprinkler system. So we have the wet sprinkler in the cooling equipment facilities and the dry one in the electrical facilities. So then the power distribution of the Lumi data center. So we have this middle voltage 10 kilovolt power distribution from the area's transformers. And our main power feeds are equipped with the automatic transfer switch, which has less than 200 milliseconds operational delay. So basically, if our primary power feed for the data center is lost, it takes less than 200 milliseconds to automatically switch power feed from primary to secondary. We have in place 8 1250 amps 10 kilovolt power feeds to our transformers, and one of those are spare, so 7 transformers installed in our data center facilities. Our middle voltage is protected by protection relays, and in addition there is this ABB ultra fast earthing switch installed. This ultra-fast earthing switch is effective combination of specific arc detection relays and associated arc quenching devices consisting of so-called primary switching element. And in case of arc flash, it's extinguished less than 4 milliseconds, which is 20 times faster compared to the standard arc protection. And as you maybe have seen what the arc flashes can cause for the power distribution, this eliminates most of the damages if that kind of event occurs in the power distribution. And we also have this ISA 61850 standard generic object-oriented substation event protocol in place, which is closed redundant fiber optics networks. And there is GPS GLONASS time servers for synchronous clocks on power distribution. So this use protocol is communication model defined by the IEC standard, which uses fast and reliable mechanism to group any format of data in the dataset and transmit it across communication network within the 4 milliseconds. It's most commonly used on data exchange between intelligent electronic devices like protection relays and switches, and it's done over the Ethernet network. So then Lumi data center power distribution, we have those 2 power feeds from the business park area transformers, and there is 2 times 40 MVA installed transformer capacity in these 2 power feeds. So there is ATS in place, and we have a 4, a little bit over 3 megawatt transformers for the IT load. So this is divided so that we have a 12 1600 amp direct feeds from our 4 transformers to direct liquid cooled compute cabinets. So there is no backup power in place. And power measurement on the direct liquid cooled cabinet is done on that level. So instead of installing the power measurement system for every single power feed of the Lumi direct liquid cooled cabinets, we only have 12 three-phase power measurement installed instead of having those over 120. And basically, this cabinet level measurement is only needed for the HPR runs, so we can combine our IT total power consumption on this higher level. Then we have in each of these IT transformer is equipped with the 250 kVA UPS backup, and this is for the air-cooled cabinet storage, network, and management, and cooling distribution units on the HPC, directly with cooled HPC cabinets. We have two 2.5 megawatts transformers for mechanical, lighting, AC, and cooling. And both of these have 500 kVA UPS backup. And also we have local ATSs for the critical cooling components like HPC cooling pumps and all the other critical cooling components. So basically those are fed from the two different UPSs, and the local ATS can transfer the power feed in case of failure from primary to secondary feed. Our low voltage system in the Europe is this 400 volts, but we have one transformer which is over 3 megawatt with 690 volts. And this is only for the district heating pumps and other district heating components like heat pumps. And as you can see from the picture, we have very nice colored power panels installed underneath the raised floor of the data center. So all of our power panels, transformers, UPSs, and power distribution is color-coded end-to-end. This includes that we have the cable labels also color-coded. So when you are operating with electricity in the two floors, you can immediately see in case of failure where this power is fed from the color of this power distribution. So a little bit about our UPS system and this fast frequency reserve market where our UPS system is connected. So our UPS are equipped with the 50 kilowatt hot swappable power modules. So there is better built-in redundancy with the smaller power modules than usually when you have, for example, two big power modules. In our case, we only lose 10 to 20% of the UPS capacity if we have a power module failure in place. All of our UPSs are with the lithium-ion battery with built-in battery monitoring system, because this lithium-ion battery was a requirement that UPS devices can be connected to this fast frequency reserve market. So this battery monitoring system is built in the lithium-ion batteries. It contains battery sampling, protection, current equalization, parallel communication, and northbound communication, voltage, temperature, electrochemical cell voltage, and other things are monitored internally from the batteries. So about this fast frequency reserve market, it's procured by Finnish national grid company called Fingrid to handle the low inertia situation. So when the frequency of in case of, for example, high voltage link or we are losing some power distribution or power production into our national grid, and this national power grid frequency goes below the 49.6 Hertz, our UPSs activates to balance this grid frequency. So the activation time needs to be below 1 second when this event happens on the national grid. And this activation period is 30 seconds, and this load lowers gradually. So it's starting with the full power and load is gradually lowered during the 30 seconds period. These UPS devices needs to be tested annually that those fulfill these fast frequency reserve market requirements. So we are doing this test every fall when this market ends. So this market is currently activated only during the summertime, and this is pretty new reserve market. So it has been implemented in Nordics in May 2020, and Fingrid procures the reserve from a national market in Finland. And there's also some circumstances when this UPS activation to the fast frequency reserve market doesn't happen. So this is that we can keep our IT production safe in case of there is an unbalance in the national power grid. So for example, when the UPS battery level is below 80%, the activation doesn't happen. If UPS, there is 2 different meters that are checking the national grid frequency. So UPS has its own internal meter, and then we have an external meter, which is sending UPS request to activate the market if this threshold is met. But if UPS internal meter isn't showing that we are below this threshold, activation doesn't happen. And of course, if UPS on battery feed, this activation doesn't happen, even though the national grid measurement shows that we are below the activation threshold. And if there is any kind of fault or alarm activated on the UPS device, activation doesn't happen. Actually, in last year, I think that there was one activation. It was caused by the nuclear power plant in the Sweden, was dropped from the national grid, and when Finland and Sweden are connected in the power grid together, and there was some event for the activating this kind of reserve in the last summer. But I think that this will be more important mechanism in the future when there is more and more unstable power production in the national grid, like wind and solar power, which are pretty much based on the how much there is wind and how is sun shining. So amount of production on those varies pretty much. So there is more information about this market on the Fingrid side where you can check the more detailed what this market is about. So this differs a little bit about the traditional reserve market where you have a big UPS system which is balancing a demand on the grid. So when the power consumption in the grid increases over the production, these kind of devices can start to balance the demand on the grid. So this is a little bit different mechanism, and this is pretty new also in the Nordics. A little bit about UPS efficiency. So in the procurement, we set pretty high requirements for the energy efficiency on the UPS system. And in our case, when we have at most 50% of the UPS load rated in the normal operation, because we have 2 separate power feeds to take all the cabinets from 2 different UPSs, and in case of power feed failure, one UPS should be able to provide full capacity to all the air-cooled cabinets. We are operating in the 50% load rate at maximum, but already in there, the UPS efficiency is up to the 97%. In eco mode, these UPSs can achieve the 99% efficiency, and in power feed failure in this eco mode, UPS can turn in the battery mode less than 4 milliseconds to avoid any disturbance for the IT equipment power feed. But this is something that we haven't implemented, so we are happy with the efficiency in the double conversion mode, which is up to the 97% in our case. So there is not so much difference anymore between the 97 and 99% to go in the eco mode. So about the power distribution, when the Lumi data center was built, so we did it in the quite short time period, and we had to test all our components before the Lumi arrived because this size of installation hadn't been done and all was new. So actually all of our main power feed components was tested before the Lumi installation started in 2021 on integrated system test. So we got adjustable load banks on site, and those was connected to the each power distribution main panels to see that all of our transformers on power distribution is working as designed. So we had a total of 3 MW of load banks installed in the power distribution, and here you can see how it was divided. So we have 2 1 MW load banks directly connected to the main panel and 1 800 kilowatt on the main panel, and the UPS side we have this 1 250 kilowatt heat load to see that our transformer can utilize its power and it doesn't get overheated with the full capacity, and the UPSs are also working as designed with the full load. On the cabinet level, we also did this power distribution test with the smaller load banks installed in the data center itself. So it was tested on the all level of power distribution before Lumi installations. Some power specifications about Lumi. Full system TDP value is a little over 10 megawatts. So our CPU partition is 231 kilowatt per cabinet. So it makes TDP value of less than 1.9 megawatt for 8 cabinets, which we currently have installed. In the HPL average, which we run on when the Lumi CPU partition was installed, we then had a 6 cabinet installed, and our HPL power average was 1.2 megawatt. So this is scaled up from that number. Lumi G, the GPU partition is TDP number, it's 332 kilowatts per cabinet, so it makes with 24 cabinet almost 8 megawatts of TDP power. HPL average on the Lumi G was in this fall when we did the phase 3 HPL runs, which was submitted to the top 500 list in the SC a couple of months ago. The average power was a little bit over 7 megawatts. Each of these GPU cabinets has 4 125 amp power feed without UPS backup, and all the CPU cabinets has 3 same size of power feeds without UPS backup. Those cooling units, which each are cooling down the 3 GPU or 3 CPU cabinets, has 263 amp power feeds with dual UPS power feed from different UPSs. So the CDU is equipped with the local ATS to transfer feed from primary to secondary feed in power loss. So it's basically always using a primary feed fully, and if in case of power failure from the primary, it turns down to the secondary to avoid the cooling loss in the compute cabinets. All of our air-cooled cabinets are with the 232 amp power feed, and both of those power feeds are UPS backed up from the 2 different UPSs. So there is redundancy in place in the UPS level also for these air-cooled cabinet and for the CDUs. Then some words about the building management and Lumi control system. So this data center building management system is provided by Finnish company Fidelix, which was established in 2002, and it has been developed as smart and reliable and widely compatible building automation systems, and it has been grown quite much in Finland in last 5 years, and more data centers are nowadays equipped with the building automation system. So the data center building management system consists of 6 substations and 1 master controller, but each of these 6 substations can be operated individually and alone without the commands from that master controller in case of failure. There is a building redundancy in substation and system level, and support protocols in this system is BACnet, Modbus, and Ambos. And most of our devices are communicating with the Modbus into the building management network. So in overall, we have over 8,500 measurement and control points in place. It's completely web user interface controlled, so there's a web user interface for controlling data center monitoring and reporting. So it's quite a user-friendly way to operate the building management system. We have also API in place, so we can read any data center metric from the building management system to the external monitoring of system or the database. So this help us to combine data from different sources to one single database to make a dashboards based on the Lumi's internal monitoring data and building management system monitoring data, and we can that way make the calculations also about the metrics. So those 6 individual substations are installed in our first floor of data centers, and all of those have local control panels and touch screens, so we can operate also building management system in case of any issue locally from the data center itself with touch screens. There is 4 of these substations for the cooling and cooling controls, and 2 are for the power distribution and power measurements. And also we have a direct connection to this district heating power plant in the area. So the control system will tell us the real-time information about district heating network from city of Kajaani, how much there is a district heating demand. Based on that demand, they can set us a power limit, how much heat we can produce to the district heating, and they can tell us to emergency power off our district heating in case of there is some issues in the district heating network. So this is basically a network we have from our building management system. So we have 2 servers in place. So these are cloned from each other. So there is a primary control server and the backup for it. Then we have a dual switches, core switches connected the access switches through the patch panel to these control devices and power measurement devices, DCR, SCRA, and all the other cooling components. Power measurement is done with the same logic, but in the power measurement we have dual connection from 2 different sources to all the components in network. Then detailed about cooling in the Lumi facilities and how the cooling is controlled. So this HPC cooling, we have 3 individually controlled cooling modules, which each consist of heat pump and 3 cooling heat exchanger. So each of these are connected to the different substations, and those are operated individually. So in case of we lose, for example, one substation, 2 of these continues running and operating without any issues. We have 3 main pumps for the HPC cooling with N+1 redundancy, so we are actively operating at 2 pumps at the time for the HPC cooling. Mechanical cooling is done by the 3 heat pumps, which each one of these have 2.3 megawatt of cooling capacity and 3 megawatt of heating capacity. So those heat pumps are able to cool down 7.2 megawatt of IT load from Lumi, and with that load, they can provide 9 megawatt of district heating to the district heating network. In addition on that, we have a free cooling with the free cooling heat exchangers and the 6 dry coolers. So each one of these are 3.3 megawatt, consists of 3.3 megawatt heat exchangers, and we have a total 10, a little bit over 10 megawatt of dry coolers installed in our roof. And even with the N+1 redundancy, we still have 9 megawatts of free cooling capacity installed. And as we are operating such high in the north, we haven't need to implement any evaporative cooling method for the dry coolers, so we are able to operate around the year with the free cooling. I will get more detail on this later. This is our HPC primary cooling loop, which consists in its liquid is primary water. We are running inlet of 32 Celsius to the Lumi's cooling units, and outlet from the Lumi varies speed based on the load, IT load on the cabinets, but it's typically somewhere like 42 degrees, but in the HPL we have seen like a 44 to 45 degrees, but in the typical operation it's close to 42 degrees, which was our design basis when we were designing our cooling for the Lumi. Total volume of this cooling loop is 130,000 liters, and it included 2 10,000-liter buffer tanks for the inlet to the Lumi. So these buffer tanks helps us to balance the variation from the cooling modules, so that we can keep the constant 32 Celsius degree to the Lumi cooling. All of our cooling pipe is done from the stainless steel, so we don't have any plastic pipe in place on our data center. Then we have this outside cooling loop, so which contains glycol. So this is installed. These dry coolers are installed in the rooftop of the building, and temperatures are 1 degree in Celsius less than in the primary side, because the heat delta T over the primary and secondary side of the heat exchanger is 1 Celsius. This HPC cooling loop can be down to the minus 25 degrees Celsius, while heat production is on in the winter time, and free cooling on the dry coolers is not operational. And I will tell later what kind of issues these can happen with the cooling, but it can get quite a cold. So that's a reason that we need to use the glycol outside. We cannot use the water. And total volume of this is 42,000 liter, and it's also made from the stainless steel. So cooling simulation and heat load test. So HPC cooling for the Lumi was simulated using this Semantum simulator-based digital twin, which gave important information for the cooling designers to adjust and simulate HPC cooling designs before the Lumi was installed and before the cooling components was in place. HPC cooling and this heat reuse was tested with 2 megawatt of total directly with heat banks before the Lumi installation. So we still have this kind of heat banks in place, which is parallel with the Lumi cooling loop, which we could use simulate 2 megawatt of IT load before the installations of the Lumi, when we had this data center construction ready and we started the integrated system tests. And also room cooling and CRAH units in the data center white space was tested with the heat banks, which we installed inside the data center. So this gave us very important information about the cooling mechanism and how we need to adjust the cooling before the Lumi cabinets will be installed. A little bit about this simulation-based digital twin we used. You can see the screen captures in here from the actual, from this digital twin. We had completely modeled Lumi cooling, HPC cooling in this system. So we were able to simulate loads, outside temperatures, load variations, and all kind of things. We could get the data how the dry coolers will increase the fan speed on the heat load changes, and how it fluctuates, how the outlet fluctuates from the free cooling heat exchangers and the heat and from the heat pumps. So this was pretty good, especially during the design phase. Our cooling designers were pretty happy for this tool selection. So they could, during the design, they had better system sizing and equipment selections. We could do faster and safer control of application tuning. So our building management system tuning could be done beforehand, even there was any cabinets installed in the data center. We could do system dynamic analysis, and we could do energy consumption estimations. During the commission phase, this had a major effect, reduction of the commission time. So we could do the adjustment of the regulation valves. We could control the application-based tuning on this simulation. This can be also used assessing impact of the planet expansion. So if the IT load increases, how the cooling needs to be adjusted if the system is expanded. And this can be also used to study exceptional cases and they impact the cooling system force. So for example, we could simulate a pump failure and that kind of things with this system. During the operation, this can be used for training of operators. This would give them the safe place to test different kind of cooling parameters before putting those into production and get understanding how this cooling works in real life. And this can be used also for the expansion planning and troubleshooting and failure diagnosis. So about this HPC cooling power steps, we had those 3 cooling modules. So from 0 to 2 megawatts, we have 1 cooling module in use. And every 2 megawatt steps, we are starting another one. And over 4 megawatt, we are running all 3 cooling modules. And always when we start a cooling module, it started on the partial free cooling, which I will explain soon, if the free cooling is not active. So we are running these cooling modules in the partial free cooling 15 minutes on the cooling module start to make sure that heat pumps get stabilized and cooling is working as designed for the Lumi. This HPC cooling control, this is an overview diagram of our HPC cooling. So basically this is outlet from the Lumi CDUs, which is approximately 42 degrees on the production. We can use the mechanical cooling and then put the 32 degree into the Lumi, or we can run it in the partial free cooling when we are using in series first heat pump and then free cooling heat exchanger, or we can bypass the heat pump and use only free cooling. Key point of operating this free cooling unit here is to having this antifreeze mixing valve, which is close to the heat exchanger, so it can make much faster adjustments on closer the heat exchanger than in the rooftop. So we can, especially in the winter time, we are able to have a pretty cold liquid from the rooftop to this mixing valve. So we are mixing the outlet from the heat exchanger, the inlet from the DCRs to maintain the 31 degree Celsius on the inlet side of the heat exchanger to keep the stable 32 degree outlet on the primary cooling loop. And this helps us to make the adjustment quicker than running all this liquid flow through the rooftop and through the heat exchangers. So operating closer to the heat exchangers, it's much faster to do the cooling operations. So this final adjustment is done with this mixing valve close the cooling heat exchanger. And we also have these buffer tanks in place, which balance inlet to the directly with HPC cabinet CDUs. And this has been pretty good investment. And as I previously told, this glycol on the rooftop can be up to the -27 degrees during the winter time, and when free cooling is not operational, when we are completely operating with the heat pumps. So then some details about the Lumi cooling and heat reuse. So we have these 3 individual cooling modules, and this is how the mechanical cooling is operated. And when we are utilizing the waste heat from the Lumi to the district heating with the heat pumps. So each of the heat pump has this 2.34 megawatt of cooling capacity, and with that amount of cooling capacity, those can generate up to the 3 megawatt district heating. This district heating network, it's primed, liquid is primed up to the 80 degrees to the district heating, and it's returning somewhere about 56 degrees from the district heating network. So we are having 42 Celsius inlet from the Lumi, which is cooled down to the 32 degrees Celsius using the heat pumps, and it's running through the buffer tanks and going to the CDU heat exchanger, and it's running up to the 36 degrees in the Lumi's internal cooling loop, which is called secondary cooling loop. Then we have this partial free cooling with heat pumps and free cooling heat exchangers and dry coolers, and this is done in the series. So first heat pump is doing the cooling, and then the free cooling heat exchanger is taking rest of the heat out from the liquid to maintain the 32 Celsius degree to the Lumi. And this is always used 15 minutes in the cooling group module startup, or if there is an alarm active on the heat pump, we are always running 10 bars of free cooling, or if the heat pump cannot keep this 32 degrees and it goes 1.5 Celsius over this set point. So basically when our outlet is 33.5 Celsius, we are switching to this partial free cooling mode. Then we have this power limit with the partial free cooling, and this is used if the district heating power plant indicates that there is not enough demand on the district heating network. So we are not able to push all the excess heat from the Lumi to the district heating network. So we need to limit our district heating power. So in this case, we are putting 800 kilowatt of power load to the free cooling heat exchanger, and 1.6 megawatt is cooled down with the heat pumps. And then they are still running in series, so all of the flow goes through the free cooling heat exchanger. And in this case, when we are taking out 1/3 of the cooling capacity of the heat pumps, we are also taking out 1/3 of capacity from the district heating. So this is the mechanism how we adjust the district heating based on the demand on the district heating network. And this applies basically in the beginning of the heating season and in end of the heating season. So usually in the spring and on the fall, when the daytime temperatures increases too much and heat load demand is too low to put all the heat to the district heating network. And this is because that power plant in the area has its minimum operational power, which it cannot go underneath it. So they need to make sure that we are not putting out district heating if they are closing this minimum operational level of this district heating power plant in the area. So then last we have this free cooling when we are bypassing the heat pumps and putting all all waste heat from the Lumi to the outside. And this is only operated when there is no demand on the district heating network, or when we have a maintenance break ongoing with the Lumi, when we cannot guarantee that we have enough load for all the time to these heat pumps to operate. I will get more detailed presentation tomorrow about this heat reuse, how it's operated and how it has been implemented in the Lumi. So this district heating specifications quickly, we have for the district heating power plant, we have 2 4-megawatt heat exchangers. So we are able to provide up to the 8 megawatt of district heating to this City of Kajaani district heating network, which is connected to this district heating power plant. And this is controlled based on the Lumi's IT load and district heating network demand. And we can operate in 2 different ways for the district heating power plant. So we can take a side flow from the return side of the district heating network. So from the city incoming cold temperature, we are preheating that to the 80 degrees, and we can push it directly to the district heating network, or we can push it to the district heating network power plant. So we are preheating their production, so they can adjust their own production based on how much we do the preheating for the district heating network. And also this business park area, this Renfosiranta business park area is utilizing this waste heat, and they have currently 1 2.3 megawatt heat exchanger installed. And this is only controlled based on the return temperature of the area district heating network. So basically, if the district heating network doesn't have enough demand, we are closing the valve when the return increase is too high. So inlet for the heat pumps, we are trying to keep it stable 58 degrees Celsius, and outlet is close to 80 degrees all the time. And connection pipes between our data center customer heat exchangers are approximately 200 meters, so it was very cost effective to implement this heat reuse in this business park area. And these cooling pipes are done in the carbon alloy steel, so those are not stainless ones. Then we have this. Yep.
Asa, I wanted to just do a time check. I didn't know how much more content you had. I know we've got a couple other.
I don't have any more. Well, I have a couple of slides left, I think. I can go through this quickly.
Okay.
Okay, so this room cooling, which we have for the air-cooled cabinets in the data center, we have 2 individually controlled modules, which consists of chiller and free cooling heat exchanger. We are currently 8 130 kilowatt GRAH units installed in the data center. These are running. Chillers are equipped with turbo core chillers, compressor, which is advanced technology to deliver high efficiency and low sound levels in compact footprints. So these are quite a good chiller devices. Those are using this R513A refrigerant, and each one of these has 1.1 megawatt of cooling capacity. So in the mechanical cooling, we are only running 1 chiller at the time. And the free cooling, same way, we have installed 1.1 megawatt of cooling capacity. And in the free cooling, we are running the both of these cooling modules to avoid this glycol loop gets too cold on the winter time. Basically, these are the volumes and the details what we are running. So 17 Celsius inlet the GRAH and outlet is 24 degrees, and there is quite a huge volumes also in these ones. So this graph quickly shows chiller's power usage. So as you can see, we are able to operate completely free cooling until about half of the April, and then we can start again since beginning of the October. We are completely in the free cooling, and there is only one very short periods in the summertime when the night times also we need to use the mechanical cooling. So during the most of the summer we are also able to operate free cooling in the night time with the room cooling. So a little bit summary about the which Pekka already covered quite much. So despite the challenges building the data center during the COVID pandemic and with global supply chain issues, the target of the data center was met. And setting up such a huge system as the Lumi hasn't been smooth sailing on the data center side also all the time. And there was some delays on the system delivery, which also caused some challenges how to optimize our heat production, which we are able to do since the full system has been now installed. But despite of these hiccups on the way, Lumi was the first Euro HPC joint undertaking operational pre-exascale system and listed on the top 500 Green 500 already in May 2022. Lots of work has been done so far adjusting HPC cooling loops, heat pumps, district heat production to get processes optimized and stable, but there is still quite much work to do. Now when we have this stable production ongoing, all the Lumi capacity is now in place. But despite all of these challenges that has been faced during the deployment and operations, our power and cooling infrastructure has been operational without any major issues now 2.5 years. So basically all of these tests that we did before the Lumi arrived was pretty successful about the operational of the operating on the Lumi in the real life. Okay, that's it. Thank you.
All right, thank you. So there are a couple questions in the chat, but I would propose that maybe we hold those to the end. And then the other thing I was considering is JP was able to join, so should we have him go through facility design and construction at this point? If there's no...
Actually, hi, Aaron, I'm already here, so.
Yeah.
So we would have you present next instead of the use cases, if that would work.
Yeah, I can do it. Sorry to be late, but
Do we need a break before?
Yeah, I recommend that we go ahead and let's just take a 4-minute break. And then also I think we will have to readjust the agenda so that we leave time for we need to end at the top of the hour, so we'll go ahead and have time for JP's presentation and then some Q&A, and then we'll close out for the day and we'll start again tomorrow. So let's go ahead and take that till 8:30. So 3 minutes now.
All right, sounds good. Okay, after our quick break, next up, as I mentioned, we'll change the agenda slightly to get into the design and construction. And so next up we'll have there we go, share. Have JP give that presentation on the construction effort. So if you're ready, JP.
Yes, I'm ready. Thank you, Aaron. So if you let me share, okay. Can you see this?
Yeah, it looks good.
Okay. All right. So Lumi facility design and construction. I will tell shortly about the history, how we managed to build the data center for Lumi and what were the kind of the design steps and the targets for us doing that. By the way, if you've seen that the green dot in a map, so that is the location where we have this Lumi in operations at the moment. All right, so Lumi data center, it's a tailor-made response to the Euro HPC data center operations and services. And how we I cannot say. Okay, sorry, this is a little bit slow. This is the project timeline, and I will concentrate the first part of that. So from the 2019 to 21 springtime, and during that we run, like I mentioned, the design and also the construction and the commission for the data center. And actually, so what are the kind of the principles when you do the data center construction and design for the HPC systems? So I highlighted these red ones, kind of the I think for the data center construction point of view, the most important when you consider your carbon footprint in your operations. So in a building phase, you need to select, are you going to do the greenfield? Of course, it's not always the option, but if it's, then you need to make the consideration between the greenfield or brownfield option. Then in a design and efficiency, you are going to target as low PUE as possible. And also, if it's possible to utilize the waste heat, then it's also beneficial for total footprint of CO2 emission. And in the very beginning, we decided that we are going to utilize the brownfield solution because we are operating in an old paper mill area, so there were a lot of available buildings for our purposes. And doing this, we assumed having reduced the CO2 footprint of Lumi data center construction by over 80%, comparing the brownfield solution versus constructing an all building for Lumi, so meaning the greenfield. And also this helps us to drive this project in a quite short project timeline. So comparing to build it everything from the scratch. And in the right side, you can see the Schneider Electric white paper 66, which describes different phases or the different elements that which generates the CO2 emission in a building phase. So utilizing the existing buildings, so we believe that we save more than 80% in emissions. So what were the technical guidelines for the design? So electricity, the full built out capacity for data center is 15 megawatt, and designed IT power capability is 10 megawatt. Which then can be allocated the liquid from 7 to 9.5 megawatt, and the air cooled systems half megawatt, from the half megawatt up to 3 megawatt. And UPS, I don't know, have you heard this from the previous presentation? But if it's the same, then yeah, probably you remember better. So UPS power capacity for IT is 1.5 megawatt, and it is N+1 redundancy. And the capacity can be allocated really flexible. And due to multiple grid connection, the site calculate availability for UPS powered IT is 5 nines. IT load is supplied via 4 independent paths. Each of the paths are supplied from 2 different directions. So main connections to the cabinet. Each of these paths can be connected on and off without disturbing other paths. And electrical distribution and consumption is real-time monitored and can easily followed remotely. So those were the kind of the electricity design principles. Then cooling, entire liquid cooled IT is connected to the district heating network, and the 95% of heat produced of the IT can be reused. In case district heating cannot take the heat load from the ICT, cooling method can be switched smoothly to the free cooling mode. And free cooling is available entire year. And the critical part of cooling system are powered by UPS. Then for the security and fire, security access control, burglar alarm and CCTV are installed, and fire alarm systems are very early sampling systems. And fire suppression, we use the gas, or we planned it in that time, and we of course we implement it. So gas suppression in the white space and meet me rooms, and then sprinkler in the technical rooms. So those were the design principles when we started the data center project. And this is the site where we have now this Lumi data center. So it's old paper mill area. So there's a lot of available power in that business park. 230 megawatt or existing transformer station power, and there is excess heat utilization on that park also. So there is a district heating network close to our data center. The river you can see in the back. So there's the river you can see there in the back. There's 3 hydropower stations very close to the city of Kajaani. And we are also running to our national HPC center in the same business park. So this was the where we started. So it like I mentioned, it's old paper mill. The building is called Rata. It looks like this when we started the project. So it was empty, cleaned, very nice. In the second floor. This picture is from the second floor. So site is adapted from former paper mill, which ensures the excellence resilience for the data center operation next 50 years and possible to grow even 10 times larger than what we built for Lumi. Site is located in guarded business park with the camera surveillance and fence around. In the data center, there are several access control security zones before you can reach the white space. So this is, I don't know, do you see my pointer, but this is the data center in a second floor. So it's a huge building, and actually there is now possibilities to grow even bigger one or to have the other data centers next to the room. So there's actually 2 floors in that big building. So the ground floor, there we have all the electricity and cooling systems in that first floor, and then second floor, there we have built the data center itself, and it is also two floors. So in the first floor in a data center, we have all the cabling and piping, and the second floor is for the IT stuff, so white space. In that same building, there's a balcony where we then decided to build the visitor center where we can host the visitors and have a meetings. So this is from the ground floor. So it was we needed to do some work for the floor and clean the place and remove some piping and the cabling, but after that it was very nice for the MET installations. And we divided that for the 2 parts. So in the lower part you can see all the electricity distribution, and in the upper part of the building here you can see the cooling part. So it is separated with the sections for the cooling and for the electricity. And totally we have rented in this first floor more than 3,000 square meters. So some pictures from the building phase. So these are in-room cooling devices in that cooling part, and also some quite heavy steel for the piping and cabling. Then for the second floor data center design, so because we had to start the design before we knew who would be the vendor for the Lumi. So we made quite a flexible design in that sense that it allows then to bring the computer number of cabinets. We didn't know those, and actually then also we have set some limits for the vendor, like inlet temperature and some weight for the cabinets and so on. But we didn't know who it would be and what kind of computer it will be inside the white space. So that's why we did that. We started with the flexible design, of course, when the vendor was selected later on, and we knew the computer itself. So then we updated the design for the data center. And the white space floor can carry, of course, we knew that those are heavy cabinets, so it is almost 3,000 kilos per cabinet what we can load for the white space. And there's a lift, we can lift those cabinets directly to the level of the white space. And as a backup, we have also ramp, which we can use if the lift is not working. And white space is allocated only for the ICT, except the cooling units, which control the air-cooled cabinets and radiated heat from the Lumi C and Lumi G systems. And all cabling, piping, distribution boards allocated in the technical room under the white space. So we take electricity and cooling to cabinets from the bottom. Here are some pictures during the construction phase. So a lot of steel beams for that building. I was surprised at how much we had to use, but like I mentioned, those cabinets are quite heavy. And you can see the size of the building, for example, in these pictures. So it's very high. So, and actually there was a crane. We could use that for the building phase. It was very useful for us. And this is that second floor. Like I mentioned, we did also this white space in the 2 floors, and all the cabling and piping are in the first, and then white space in the second. And totally, we have rented in this second floor a little bit more than 2,000 square meters. And these are the pictures from the data center first floor, where we have this piping and cabling. This is not good picture at all, but I wanted just highlight that we run this project in about 21 months, starting from the early design, and so at least I think that was quite pretty good result if we consider that we did that during the COVID time. So of course that somehow affect to us, but not so much, luckily. And this was kind of the results. So it looks like this when we put some lighting on. And like I mentioned, there is this balcony where we have this showroom. We can keep the presentations for tens of people, and there's a meeting rooms and so on. Then we probably did something right, because we have win awards. So for example, Data Center Design Innovation Awards 2021, and then this year a Green Data Center of the Year awards. And of course Lumi has also granted with the awards. So seems that we did something right with this project here in Finland and Kajaani. And some remarks in the end. So we run it this data center project under the budget in a planned schedule. We did the probably most sustainable HPC data center. All visitors who have visited our site like what they see there, and we have a lot of visitors this year, maybe 1,200 visitors. And we had only one accident, minor accident during the construction phase. So I'm happy with that also. Thank you. I think that was my presentation from the data center facility.
Excellent. So I know we have a few questions in the chat. Maybe we loop back to those for ASA, and then also if there's any questions about construction or the Lumi system. At this point, we'll just go to Q&A. Looks like, yeah, there was a question on the chillers, so that got answered. There were a couple questions about the monitoring system and the digital twin. So I don't know if Asa, if you want to comment on those. They were from Thomas.
Yeah, about the rates that or how the power measurement, for example, are saved, we can adjust that. So during the HPR, we can make it down to 1 second on the necessary power readings for the HPR power submit. But in the normal operations, it's good enough if you have, for example, in the cooling temperatures and that kind of values once in a 30 second or once in a minute. So it can be adjusted. In overall, we are storing all the historical data currently from the data center so far in the our building management system database. So since day one, we have all the data stored. And about the latency, given that you use it for the emergency power off for the district heating, actually it has been never activated, luckily. So it's only in the true major incident in the district heating. So if they need to shut down our district heating immediately, for example, in the case that there is a leak in the district heating network and it's happening, for example, outside of office hours, they are able to do that, but it hasn't been never actually done in the production. Of course, in the system test, we did the test, and it's direct connection between these two building management system or control system, so there is not much latency about it. It takes some time from our valves to adjust from the mechanical cooling to free cooling, and I will show tomorrow some example what happens when we go directly from mechanical cooling to free cooling in the cooling wise. And do we have control Lumi equipment, for example, slurm or rubber limits for the signals for only for the heat pump? So we are not controlling Lumi power usage based on the district heating. So we are only controlling our heat production. So Lumi is as fully utilized as there is jobs running. And have we done comparison between the digital twin simulations and accuracy of predictions with reality? No, we don't have done actual comparison between these two of these datasets. We actually used this digital twin mostly in the design phase of the data center when we did the final component selections and when we had a cooling designs ongoing without knowing which system we will have, and then we did the adjustment for the cooling designs when the system was procured. So this digital twin hasn't been used pretty much since data center started operation.
Let's see. Another question about biological problems in warm water. That's for stay tuned for tomorrow.
Yeah. Yeah, I will include that section also tomorrow, my lessons learned.
Let's see. How would you compare to others, Oak Ridge and others regarding UPS capacity?
Actually, we visited in the Oak Ridge lately, but I cannot recall how much UPS capacity they have in the frontier. So I haven't done any comparison between UPS capacity. But we have, let's say, enough capacity for this installation, and it has been pretty good choice with these devices.
If I recall, you have 1.5 megawatts of UPS capacity.
In total, we have this 2 megawatt of UPS capacity. So JP had this design basis on his slide, but we end up with the 4 250 kilowatt UPSs for the IT, and we have 2 500 kilowatt UPS for the mechanical and cooling. So in total, we have now 2 megawatt of UPS capacity in place, which 1 megawatt is used for the IT and cooling units on the Lumi cabinets.
Yeah, I would say at NREL, you're very similar to what we cover: cooling equipment, ARCs, racks, CDUs, and storage, and it's about 10%, a little more than 10% of the system.
Yeah.
So I think, at least from an NREL perspective, it's similar. Let's see, we've got just a couple minutes left. Any other questions?
There was one question that I left unanswered. So did you use a proxy for HPC operations as load input for a simulation? Actually, no. It was pretty surprising for the electrical and mechanical cooling designers that when I first saw the simulation and they did a ramp up in the power within the minutes from the minimum to maximum, and I went up into that meeting and say that it will happen in seconds, not in the minutes. Then they had to adjust and make some more adjustment for the cooling design, and they didn't have the exact understanding that how quickly power can increase in this size of GPU system if the full system is utilized from the 0 nodes up to the maximum nodes. But we didn't have any real life HPC operations load as input for the simulation.
And then it looks like we've got a last question here about power measurements at the node level or the cabinet, and if there's any noticeable differences.
Actually, we are doing power measurement in the rectifier level of the cabinet using the Lumi's internal Kafka stream to get that data out. And also we have this building management measurement in the downstairs where this directly with cooled cabinet has been measured. And this is something that I have been compared, and those are very close. Very closely same. Of course, we have some cable losses involved when we are measuring from building management system, because there's a long feed cables going downstairs to upstairs, and further there we have a power feed cables for the Lumi cabinet itself, which are pretty long also. So there is some cable losses involved. So there's slight difference between these two power measurements, but the closer the cabinets we are, more accurate it is. So this rectifier level power measurement is pretty accurate.
All right. Well, I think we'll call that for today and reconvene tomorrow. Just some quick wrap-up logistics. A reminder that this is the workshop website. Presentations will be uploaded. And special thanks to everybody on the committee. There was quite a number of us involved, and we will reconvene again tomorrow. Probably juggle the agenda just slightly given some of the content we want to cover. And thank you all very much.
Thank you.
Yes, thank you.
Thank you. See you tomorrow.
Thank you.
Bye.
Thank
Bye.
you.